Astrophysics, the study of our universe, can feel detached from our lives here on Earth. But it doesn't need to be. Here in Potsdam, we've recently hosted a large conference with researchers from around the globe. In the process, we've asked some experts to break down key astrophysical concepts, from galaxies to cosmology. In this episode, we'll meet Dr. Marcel Pawlowski and Nick Heesters. They'll discuss satellite planes, one of the biggest unsolved mysteries in the nearby universe.
I'm Marcel Pawlowski. I'm a junior research group leader at the Leibniz Institute for Astrophysics here in Potsdam, working with a really smart team of people on questions about dwarf galaxies and how they compare to cosmology and our expectations of how the universe formed and evolved. Already in 1976, there were two papers talking about the distribution, the spatial distribution of satellite galaxies around the Milky Way. So we only knew of a handful back then, but it turned out that they all were distributed along basically one band on the sky. And if you look at the Milky Way from outside, it would look like they are all in a plane. So it was kind of a plane of satellite galaxies around the Milky Way. A little bit like the planets orbiting the sun in a common plane. Not quite as strict, but similar. So that was just an observational fact back then, and satellite galaxies should distribute around the galaxy. Nobody really thought about that too much until we had the first cosmological simulations. So when you take a computer simulation of the universe and you pick out an analog of the Milky Way, you can look at how are satellite galaxies in this simulation distributed around the Milky Way. And it turns out they are pretty randomly distributed. It's kind of a big, fluffy ball of satellite galaxies which move in all kinds of directions. And that's very much at odds with the observed situation, where you had a number of satellite galaxies. By 2005, there were 11 satellite galaxies known. Almost all of them were in a very narrow planar distribution. That's also perpendicular to the disk of the Milky Way. So that in itself was kind of a problem, or suggested to be a problem for the cosmological expectations. And as time progressed, more measurements were made, and then using these proper motion measurements, so the motion of satellite galaxies on the sky, not just towards or away from us, so you have 3D information where they are going. That then allowed us to test, are these satellite galaxies staying in that plane, or do they move out? From cosmological simulations, we would expect them, even in the rare cases where they have a flattened distribution, they would move out of that relatively quickly. So it should just be a chance alignment. What the proper motion measurements told us is that most of the satellite galaxies of the Milky Way seem to move along this planar distribution in the same direction, which, if you compare it, happens in less than 1 in 1,000 galaxies in those cosmological simulations. So this is kind of problematic for the model, but also very interesting to just study for the Milky Way. There's a well-known satellite plane for the Milky Way, which, by the way, I call the vast polar structure because it's really extended. So it's stretching from the Milky Way inner regions itself out to the edge of the dark matter halo of the Milky Way. It's polar, so it's perpendicular to the Milky Way disk. And it's clearly a structure that's not only there in spatial distribution, but also in the motions. Now, beyond the vast polar structure, or beyond the plane of satellite galaxies of the Milky Way, there have been other studies looking at this in external galaxies. Because, the Milky Way is an outlier in our expectations, but maybe the Milky Way is special. We all like to be special, right? And maybe this is just the special feature of our Milky Way. So people have looked at it in external galaxies. Our nearest neighbor is the Andromeda galaxy. That's also a very massive spiral galaxy. And for that one, we know the satellite distribution pretty well. And it turns out that among the satellites there, about half of them are also distributed in a very narrow plane. That plane is seen almost edge-on. So if you look at Andromeda, we can see this plane like on the edge. And even though Andromeda is much further away, it is difficult to get proper motion measurements, so 3D information for the motions of satellite galaxies around Andromeda, it is still very easy to get line of sight velocities. So just to measure the spectroscopic redshift of a satellite galaxy, you know whether it's approaching you or moving away from you. Now, if you see a plane of satellites edge on, that can tell us whether they are moving in the one or the other direction along the plane. And it turns out that all the satellites on one side of this Andromeda satellite plane are redshifted, while the other ones are blue shifted. Well, not all. Out of 15, 13 have this coherence in line of sight velocity. And that's indicative of a possibly rotating plane. So it's similar to disk galaxies. When you look at a spiral galaxy somewhere and you measure its rotation curve, you can do that. You see that one side is approaching us, the other one is receding from us. It's a very narrow, flat structure, so that's, of course, interpreted as a rotating disk. And you can do the same exercise for the satellite plane of Andromeda and interpret it that way. Of course, we can't be 100% sure because we don't have the 3D information of the velocity. But there have been now 2 measurements for satellite galaxies on this plane, which indicate that they are indeed consistent with moving along this plane in a coherent sense. So that's the second example beyond the Milky Way satellite plane. And you can also make comparisons to cosmological simulations in the same way. You kind of treat the simulation as if it would be an observed Andromeda system. You measure the flatness of the satellite distribution, you measure the coherence in line of sight velocities, and you again find of order 1 in 1,000 outlier seems to be realized right next to us. So only 1 in 1,000 simulated galaxies shows a similar degree of coherence. Okay, so 2 examples, but maybe the local group is special. So let's look further out. And the other really big case is the Centaurus A galaxy. So that's even further away, about 5 times further away than Andromeda. It's a massive elliptical galaxy, so now for a change it's not a spiral galaxy, but more roundish object. And it has a well-studied satellite galaxy system. And it turns out that system is also somewhat flattened. It's not really a plane. So the axis ratio we see on the sky is more 1 to 2. So it's a flattened ellipsoid as far as we can tell. The distance information to these satellite galaxies are not as good because the further you go away, the same uncertainty basically translates to much larger absolute uncertainty in the distances. So if you look at the Centaurus A satellite galaxies, you find them to be somewhat flattened on the sky, but you can also look at the line of sight velocities and you see that, again, those on one side preferentially move away from us, those on the other side preferentially move towards us, so it's again looking like it's a rotating structure. And you can do the same exercise, compare that to cosmological expectations, so you again pick analogs of Centaurus A, which is now somewhat more massive. You study the simulated satellite systems there in the same way as you treat the observed one, and you find, again, it's something of the order of point a few percent outlier. So again, 1 in 1,000 of order unlikeliness to find this, and that's the third case we have. So we have these 3 satellite galaxy planes. We have the Milky Way, the Andromeda Galaxy, and Centaurus A, where we have well-studied satellite galaxy systems, which all indicate there's a flattened distribution and some coherence in the motions along this plane. And all 3 cases are kind of where in our cosmological simulations, which means there's something going on. We are missing something. There have been studies to look at this in an even larger sample, so there are a few cases also where we don't see any evidence for satellite galaxy planes, so not every galaxy seems to have them. But looking at more distant galaxies, it's also much more difficult to find them because you kind of rely on seeing them close to edge on, because if you see them face on, you wouldn't notice, right? It's kind of spread out all over the sky. And it's kind of important to have velocity information, which for these faint dwarf galaxies is pretty hard to get at large distances. Nevertheless, there have been some statistical studies that suggest that maybe 25%, maybe even 50% of all satellite galaxies live in those kinds of planar flattened structures. And well, that's a very active area of research where we are trying to push the boundaries to really build a good understanding of what this effect is like in the real universe to then properly compare to cosmological simulations, not just on a case-by-case basis, but over a larger number of host galaxies.
My name is Nick Heesters. I'm a first-year PhD student at EPFL in Lausanne in Switzerland. What I'm interested in is looking indeed further out, outside of our local group, outside of our local volume, and to see if there are such structures in other satellite systems as well. To do this, I have been looking at over 2,000 dwarf galaxies in these more distant systems in the so-called MATLAS survey, and to look if there are hints of flattened structures around these more distant systems. So the issue here is really that for these 2,000 dwarf galaxies, we don't really have distances or velocity information for the most part. So this analysis had to be done in 2D in a first step, and we just looked at really the spatial distribution, assuming that all of these dwarf galaxies are members or satellites of their host galaxy, of the targeted host galaxy. And indeed, we find that about 30% of the satellite systems that we looked at show such significant flattened structures. Now, as I said, that is only half of the story, because the real issue in lambda CDM is not the flattening alone, it's the simultaneous co-rotation that's really puzzling. To really get to the bottom of this issue, we are doing follow-up observations, getting spectroscopy, so figuring out how these satellites are moving around their host galaxy. And we can do this by looking at their velocity that we get from these observations and then comparing that to the velocity of the host galaxy. And if they're, first of all, we have to figure out if they're actually part of this satellite system. If the velocity is sufficiently close to the one of the host galaxy, then we can confidently say that they are satellites of that system. And then in a second step, we can look at these velocities in comparison to the one of the host galaxy. If we would observe such hints of co-rotation in a lot of these systems in, beyond the local volume, then it would pose a significant problem for our standard model of cosmology, because that is not what we expect at all.
These plans of satellite galaxies, you don't find them in cosmological simulations if you just do a one-to-one comparison and treat model galaxies in the same way as observed ones. So there needs to be some way of forming them. I mean, we know they exist, so they have to come about somehow, right? And there have been a number of suggestions. So for one, if you stay in the cosmological framework, cosmological simulations indicate that we live in a universe that forms hierarchically. So you first form small galaxies, and they merge together, they form bigger galaxies, and that happens in a very hierarchical way. So a big galaxy still creates smaller galaxies, and that's how it gets its satellite galaxies usually. But it does that not in a completely random way, but from preferred directions. So there's what's called the cosmic web. So it's kind of a filamentary structure of mass distribution around a galaxy that tells you that from some directions galaxies preferentially fall in. And that can give you some degree of anisotropy, so of kind of order in the distribution of satellite galaxies, and also gives you more coherence in their motion. That has been suggested as a possible solution for this problem. The issue is that this process is already present in the cosmological simulations themselves. So while it does cause some anisotropy of the satellite systems, the effect doesn't seem to be strong enough to form these very, very pronounced structures that we observe. Another possibility is the inflow of groups of galaxies. So if you have several galaxies falling in together, several dwarf galaxies falling together onto a Milky Way, let's say, they are first relatively compact, and then they get split up and they distribute around the galaxy. But they would still kind of remember that they came in from a similar direction, which means they will follow a similar orbit, they orbit in a similar plane, they will follow orbits in a similar direction around the host. So that can also boost the coherence of a satellite galaxy system, which is again an effect that should be present in those cosmological simulations and has been studied there, and obviously isn't strong enough in the way it's implemented. But of course, maybe the simulations are lacking something. Maybe there's a way of boosting the signal. Maybe there's special groups of satellite galaxies falling in, particularly rich groups, where you have a lot of luminous dwarf galaxies that then can form such a structure. One example of that would be the Large Magellanic Cloud, which is the most massive satellite galaxy of the Milky Way. It's approaching, in the mass estimate, a 1-to-4 ratio in masses between the Milky Way and this massive satellite galaxy. And so this Large Magellanic Cloud brings in a number of satellites of its own. And those, of course, then follow the orbit of the LMC, and they move in the same direction. And since we know that the LMC is moving along the plane of satellite galaxies, that definitely contributes to this effect. The problem with that, well, it's not really a problem maybe, but it's a scenario specific to the Milky Way. So to also explain satellite planes around Andromeda or Centaurus A, you need some other mechanism, or at least another specific scenario for those. One possibility there is a merger of massive galaxies. So even more extreme than the 1-to-4 mass ratio between the Milky Way and the LMC, you could have an almost equal mass merger forming a galaxy. That has been suggested to have happened to Centaurus A not too long ago, a few billion years ago. There might have been a major merger forming this elliptical galaxy. And in that process, well, the galaxies bring in their own satellites. So one idea was that maybe the fact that two galaxies fall together, maybe spiral in, adds to the angular momentum, so adds rotation to the satellite galaxy system, and then that could produce some observational effect that is similar to what we see in Centaurus A. Turns out that doesn't really work that well in cosmological simulations. You can construct kind of toy models where it seems to work, but as soon as you try to do this in this whole context of a cosmological background, the effect isn't strong enough. But there's another effect if you look at merging galaxies or interacting galaxies. That's the tidal effect on the galaxies themselves. So imagine you have a spiral galaxy that collides with another one. Spiral galaxy is rotating in a certain way. In the same way, it's orbiting around the host galaxy. So you produce strong tidal effects. That means there's material whipped out of the galaxy. So it's a bit similar to the tides on Earth, where, well, the sea level rises and lowers by a few meters because of the moon orbiting around the Earth, for example. But in space, this is much more violent process. So you really whip out arms of gas and stars from a galaxy. And along those tidal tails, they are called, you can form new galaxies. So you can form new stars, and they can then form kind of dwarf galaxies, which would align along this tail that's whipped out of the galaxy and move in the same direction. So this scenario can easily explain the coherence in motion and the nice alignment in a common plane of dwarf galaxies if they are tidal dwarf galaxies. And so it has been suggested, even the first papers on the spatial distribution of the satellite galaxies of the Milky Way by Donald Bell in 1976, that already suggested there might have been a breakup of a galaxy that led to such a formation. But again, if you look at cosmological simulations, this effect doesn't seem to work because these tidal dwarf galaxies that form out of the tails whipped out of massive disks, right? They shouldn't have dark matter. Because in the disk material, the dark matter around the galaxy is kind of a big blob that's randomly, with dark matter particles that are moving randomly, whereas the disk material is nicely orbiting in a common plane. So if you form this tidal tail, there's almost no dark matter in there. So these tidal dwarf galaxies cannot really contain dark matter. Yet we observe satellite galaxies around the Milky Way and also the other galaxies, and they have high internal velocities, so they can only be stable if they have dark matter in the cosmological standard model at least. So that doesn't seem to work either. One possible way out is kind of relatively extreme. So you can say that maybe we give up on this whole idea of dark matter and instead say, let's adopt a modified gravity model. So what we think is dark matter is actually our misunderstanding of the laws of gravity. So on the scale of galaxies, gravity has a stronger effect, acts more strongly, so the same mass produces more force. And then you could understand tidal dwarf galaxies looking as if they have dark matter, just because the same law of gravity applies to them. But that model, of course, has its own plenty of other issues, and we are kind of still lacking a full model of cosmology in that. So it's a trade-off. If you want to solve this plane of satellite galaxy model that way, you open up a lot of doors for additional questions and problems that you still have to explain. So I think right now we don't have a perfect model, a perfect scenario to explain these planes of satellite galaxies. I think that's also why it's crucial to look at this in a broader sense, to look at it for really a full population of galaxies and look at it statistically to see, is it really a problem for all galaxies, or is it a problem for a few specific systems? And that can tell us whether we really have to look at specific formation scenarios, the history of the Milky Way, the history of the local group with Andromeda and the Milky Way, or if it's really a very broad common problem that can be better addressed by saying, okay, what's missing in the cosmological simulations? What do we have to change there to make, say, filamentary accretion or group inflow more effective? You can find me online. I have a website with more videos and articles, but you can also look at Twitter or Blue Sky. My handle is 8 minutes old, and I'm looking forward to interacting.
So if you want to know more, you can find me on Twitter at Heesters_N.